Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the order of groups. So the order of a group or subgroup, which is denoted like this, is simply the number of elements in that group or subgroup. More interesting is the order of an element. So the order of an element is the minimum value of k such that this or this is true. If the group operation is multiplication, the order of an element is how many times you need to multiply it by itself to get 1. And if the group operation is addition, it's how many times you need to add the element to itself to get 0. Notice, of course, this is the multiplicative identity and this is the additive identity. So it turns out that groups can have infinite order. We've seen groups like this before. For example, the general linear group, which is the group of all n by n invertible matrices, that's infinite. There are infinitely many of them, so the order of that group is infinity. So too, an element can have infinite order. If we look at the normal integers under addition, the order of 1 is equal to infinity. It doesn't matter how many times you add 1 to itself, it will never ever give you 0. And that's why it has infinite order. So it is possible for an element to have infinite order if the group itself has infinite order. Now, Lagrange's theorem is very helpful when we're looking at the order of groups. It says that for any subgroup, its order divides the order of the whole group. That's what this says here. Order of H, a subgroup, divides order of G, which is the whole group. There is an analogous rule for the order of an element. It turns out the order of an element also divides the order of a group. So let's look at why that is. Now, if we have a group G, any element in that group generates what's called a cyclic subgroup, and this is how we denote it here. So a cyclic subgroup either looks like this or this. This is what it looks like if the group is under multiplication. So the cyclic subgroup generated by G is simply all the powers of G. It turns out this will always be a subgroup. Now, in this case here, the order of G must be k plus 1. The only way this can be a subgroup is if I multiply by G again, I get the multiplicative identity. So the order of G in this group is k plus 1. Notice that k plus 1 is precisely the number of elements in this cyclic subgroup generated by G. And it works the same when the group operation is addition. In this case, the cyclic subgroup is all the multiples of G. So in order that this is a subgroup, if I add another multiple of G, I would have to get 0. Once again, this subgroup here has k plus 1 elements, and that is precisely the order of G here. So the order of an element is precisely the number of elements in the cyclic subgroup that it generates. So consequently, because of Lagrange's theorem, which tells us that the order of any subgroup divides the order of the whole group, it must also be true that the order of any element divides the order of the whole group. And that can be very useful when calculating orders. Now, just a point on this cyclic subgroups, it turns out that if it is ever the case that an element and the whole group have the same order, then the group must be cyclic. So to give you a concrete example of these cyclic subgroups, let's look at the integers modulo 10 under addition and the subgroup generated by 2 and 6. Remember, this notation means it's the cyclic subgroup generated by these elements. So the cyclic subgroup generated by 2 is just the multiples of 2. Now, to be a subgroup, it has to have 0 as well. 2, 4, 6, 8. Now the next multiple of 2 is 10, which takes us back to 0. So if I wanted to find the cyclic subgroup generated by 6, well, again, I have to have 0. And then I would have 6. The next multiple of 6 is 12. So that's equivalent to 2 mod 10. Plus 6, you get 8. Plus 6, you get 14, which is 4 mod 10. And then if you add 6 more, you're back at 0. 14 plus 6 is 20, which is 0 mod 10. So note here that these two cyclic subgroups are exactly the same. So we said before that any element G denotes its cyclic subgroup, but that doesn't necessarily mean that the number of cyclic subgroups is equal to the number of elements of G. Sometimes you have the case where cyclic subgroups generated by distinct elements end up with the same subgroup. All right, let's now look at an example in which we calculate order. So we're going to calculate the order of the element 4, firstly in the group of integers under addition, modulo 59, then in the group of non-zero elements under multiplication, modulo 59. So the order of this group here is 59. So Lagrange's theorem tells us that the order of 4 has to divide this. But 59's prime. The only two numbers that divide 59 are 1 and 59. So rather than continually adding 4 until we get 0 in this group, we've narrowed our choices considerably. Now, the only element that has order 1 is the identity element. Now, clearly 4 is not an additive identity in this group. It's not equivalent to 0 mod 59. So that leaves us only possibility is the order of 4 is 59 in this group. That means you need to add 4 to itself 59 times in order to get 0 in modulo 59. Of course, we know that 4 times 59 is equivalent to 0 in mod 59. All right, let's now find the order of 4 in this group here. So this group actually has order of 58 because only the non-zero elements in mod 59 form a group under multiplication. We can't include 0 because it has no multiplicative inverse. So to find the order of 4, let's use Lagrange's theorem. It tells us the order of 4 is a number that divides 58, basically a factor, a positive integer factor of 58. So the numbers that divide 58 are 1, 2, 29, and 58. So it's really helped us narrow down considerably the possible orders. Now, once again, 4 is not the identity here. It's not the multiplicative identity in this group, so we can exclude 1 straight away. So let's check if its order is 2. Well, 4 squared is 16, and it continues to be 16 in mod 59. So its order is not 2. Then we might try 29. Well, 4 to the power of 29 turns out does give us 1 in mod 59. So the order of 4 in this group is 29. Now note here that 58 might seem like the order because 4 to the power of 58 also is equivalent to 1 in mod 59. But as I wrote on the previous slide, the order is the lowest possible number. Because this is a group under multiplication, we're looking at the smallest number of times 4 needs to be multiplied by itself to get the identity. So even though 4 to the power of 58 does give you the identity, 58 is not the smallest such number. So we write order of 4 in this group we're talking about is equal to 29. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.